Good afternoon, everyone.
Good afternoon.
And welcome back this week. Last week, the last time we met, we were talking about substituting the t-score for the z-score in finding out where we stand as far as how confident we are in our scores. And anytime we're talking about how confident we are in something, we're talking about looking at the standard error, remember, and why that is standardized, okay? Is this all ringing a bell for everybody? Okay. And so in your test, we use z, and this, we started to use t. And do you remember, when we want to find out where we stand, we use this formula? And why are we using t anyway? What is it about t that makes it attractive to us?
N is less than 30.
When the n is less than 30, okay, when it's less than 30, t becomes an attractive test, okay? And the fact of the matter is, if you go to your table, and if we could just zoom in on the table here. There we go. Now let's look over here. Let me point this out to you. Okay, this is the column for being 95% certain, or an alpha level of 0.025, because this is a paired sample or two-tailed test. Okay, we see that after we pass 30, that our number corresponds to what the z-score would be for 95%, doesn't it? Or for half of 95%. Okay, 1.96. Remember, that was a magic number. It's like almost like a Fibonacci number, right? Okay. So t is a very attractive number for us when we're talking about samples where n is less than 30. Let's get an eraser. So let's just go over this one problem, and then we're going to move on. All state inspection stations. Does that sound familiar to you? All state inspection stations were tested, and we had an n that equaled 20. Okay, there's 20 stations that we're testing. Okay, and the whole population mean, the mean of the population, okay, is 70. Okay. Our score, us, the mean of us, let's make it 75, okay? And the standard deviation is 10, okay? And I want to be 95% certain. That is the level of certainty that I want. Some of the things that we're going to need, because we're going to be using t because n is less than 20, so we're going to be using a t-score, correct?
Correct.
So one of the other things that we need here is we need degrees of freedom, and we also need the standard error, right? Those are the two things that are missing from the equation here. What was the formula for degrees of freedom? Equals n minus 1. And this is an adjustment that we make when looking at the t-test, okay, because of the distribution is not a normal distribution. It's not as high as a normal distribution. It's flatter. It's a flatter distribution because there's less numbers. Just for review here, this stands for frequency, doesn't it? Mm-hmm. So when we're looking at a normal distribution, there would be a high frequency here, right? Where the mean, the median, and the mode cross, the frequency would be high. So that's because the number of n, the numbers in n are high. In the t-test, our frequency gets lower. So we have more of a distribution that looks like this, okay? A flatter distribution. So we have to make some type of adjustment to n, okay? And the adjustment is these degrees of freedom, n minus 1. There's a lot of debate not debate, but a lot of different definitions of what this degrees of freedom amounts to. But for t-test, we could say it's an adjustment for the frequency being lower. The other thing we need to know is the formula for standard error. So let's just, first of all, before we go to standard error, let's do degrees of freedom. What is n? Is 20, right?
Yes.
Minus 1. So our degrees of freedom in this example are going to be 19. So we need to know that, don't we? And then we need to know the standard error. And the formula for the standard error is standard deviation divided by the square root of q, right? N. N. Okay, and what is the standard deviation here? 10.
10.
And the square root of 20 is some number that I don't have. I do have a calculator. I brought a calculator this week, but let you do the math. So this would be 10 divided by 4. What is it?
4.47.
4.47. And that's going to equal
2.24.
2.2. Let's make it 2. I have in my notes 2.23. So can we keep it that way? Is that close enough? 2.23. All right. So now we have standard error. We have degrees of freedom. We have everything that we need here to determine this, except one thing. We don't know what the value for t is at 95% yet, right? Because we have this formula now, okay? And the formula is t times the standard error plus or minus the mean. And what mean are we plussing or minusing it from?
Your score.
Okay, right. We want to be confident in my score, so it's the mean of us, right? How we're doing. Okay, we don't have this value yet, do we? But we have everything we need to find this value. How do we find this value, Eleanor? How do we find t? We have degrees of freedom, okay? And we have the 95%. What do we need to do here? How do we break these two things down? We know degrees of freedom. We know we want to be 95%. How do we break this down? What are we going to do next?
Do we need to look at our t distribution table?
We do need to look at the t distribution table. Okay, but the first thing is we have to convert this 95% into an alpha level, which is the residual between 100% and the 95%, which is 5%, right? The alpha would be 0.05, but however, your table only shows half of the distribution, right? A one-tailed test. We want to show it for a two-tailed test. So this number here, we've got to divide by 2, and we get 0.025. Okay? You got that? So we know now 95%. We got to look in the 0.025 column. And why don't you just write 95% above that column? Did you do that already last week?
Yes.
95%. Okay. And at the 0.01 column, what did you write up there?
98.
98. And we don't have a 99. Yeah, we do.
Yeah, we get the
Your 0.005
Yes.
is 99%. Okay? You got that written in? All right. So now we know what column we have to look under. And we also know degrees of freedom. And degrees of freedom, as you remember, is in this far left column. You see DF on the top? So what degrees of freedom are we looking for, Lazarus?
Dudgy, I'm so lost right now. I'm still trying to figure out where you got the 0.5 from, because in my book, I got it labeled as 90%.
Right, right. But I'm just saying, okay, that's a good question. Let's go back to this. I'm right up here right now. If I want to be 95% certain of something, okay, what's the alpha level that I'm looking at? In other words, the amount that I'm going to allow myself to be wrong, okay, is 0.05. It's the residual. That's the alpha level. It's the residual percentage between 100 and how confident you want to be, your confidence level. So you want to be 95. I want to be 95% confident of my mean here, right?
Right.
your chart only, just like the Z table, remember the Z table only showed half. So when we wanted 95%, what did we have to do?
Divide it.
Divide it. So we got 0.45 something, right? Okay. Here, this table doesn't work in the same way. It works a little bit different. It works with that alpha, what we call alpha, okay? Our significant, or another way of saying alpha is significance level, how significant our results have to be, okay? So in this case, this alpha, okay, is our significance level. It's actually 0.05, but because this is only one tail, we have to divide it by 2.
Okay.
We have to take half. So it's 0.025. And you should have that on your chart, because we said this last week.
Okay.
I said at 0.025, put 95% above there. So you know that that's the 95% level. And just to prove it, Lazarus, if you go all the way down to the bottom of that table, where you go to infinity and beyond, right?
Mm-hmm.
You're at, does that look familiar as a z-score, 1.96?
That was half of.
No, it's not half. If you go to the z-table,
95 divided by?
it's half of 95 as a z-score. Okay, if you find the percentage, well, let's just go to to your z-table. Go to 1.9 and over to 0.06.
.475.
Right. That's, again, half. We would have to multiply that by 2, and you're going to get 95%. Okay? Do you all see that? Okay, we're all square with that? Okay. Of course, we're going to move on here. Okay, so what I need right now, we know that 95%, I'm going to be looking, if we could zoom in on the table, again, let's zoom in. And I'm going to walk over to the, that's good. We know we're going to be going down this column, and we're going to go into 19 degrees of freedom, right? Because n minus 1. We have 20, n minus 1. So we went to 19, and we're going to go over to 0.025, and it comes to 2.09. That's my t-score. That's my value for t. So now I can put in the value for t, which is 2.09, times the standard error, which is 2.23. And now I'm going to get a number that I'm going to add and subtract to my mean. So let's do the math here. 2.09 times 2.23. 4.66? 4.66. So now, let's go back to my diagram, my t-distribution. And the mean that I'm looking at here is how confident I am of my mean, which is my score. Okay? And my score was, because I erased it and I changed it from my notes, 75. Okay? On this side of the mean, I'm going to add 4.66. Okay? And on this side, I'm going to subtract from 75 4.66. Right?
Yes.
So this would be over here. At this point, I'd be at 79.66. And I'm always good at the adding side. It's the subtracting side that I need somebody's help with, the calculator. 75 minus 4.66.
70.34.
70 point, who's selling?
34.
Wendy?
Yeah.
Thank you. Okay, now, what would I say here? I am what? Well, say it outside, Mr. Reddick. Out loud. I say it outside. Go outside and say it.
You're 95% sure of being between 7.34 and 79.66.
I'm 95% certain that my mean is between 70.34 and 79.66. Make sense? Okay. we are going to go a quantum leap forward. It's going to seem that way anyway. We're still going to be talking about t-tests. Okay. Do you remember my little diagrams from last week?
Yes.
Okay, let's say that these are t-distributions. And what we're to with the t-distribution, and we talked about this last week, is we talked about accepting or rejecting the null hypothesis. And the null hypothesis is the hypothesis that nothing is happening, okay? That there is really no difference between your sample, okay, and your population, okay? There's nothing unique. There's nothing significant about it, the uniqueness of it, okay? So if it's nothing unique, that means that my mean of my, let's do it this way. This one's a little bit smaller. The mean of my sample is not going to be too far distant from the mean of my population. Or we don't have to compare the sample to the population. We could be comparing two samples. Let's say I'm looking at two samples. I'm looking at 20 health inspection stations in North Carolina against 20 health inspection stations in South Carolina. So are they different? If they were different, then the mean of one might be pushed over significantly, okay? As opposed to they're not that much different. Now, either way, it can be very valuable information that we could be getting. We might want to see that there's not a difference. So we might want to accept the null hypothesis. We might be hoping for the null hypothesis. I once did a study about, and I may have mentioned this already, I'll hear it when I view the videotape. I always said that thing 5 times, that I did a study about elites in Congress. What I wanted to show was that the majority of Congress is made up of people that are elites. People that go to Ivy League schools, that have a professional degree, doctor, lawyer. I had all this criteria. Had families that were very heavily involved in politics, ward leaders, etc. A couple of other criteria that I had. Well, my hypothesis was that there was no difference between the elites that I identified, a subgroup of all of Congress, the 535 members of Congress, and all of Congress as a whole. All right? So my theory is there's no difference, that they're all elites, that essentially they're all elites if you look at it. And frankly, that's what I found, that there was very little variance, okay, between my sample of elites and all of the members of Congress and how they fit into that criteria. Okay? It would have to be pushed over a little bit more, okay, more than 0.05 or more than 0.025 when you're looking at a two-sided test, two-tailed test, okay, for it to be, for me to reject, the null hypothesis. Now, if you remember, if we go back to the chart, when we're looking at t-tests, and I actually made a mess of this. Stop. Okay, right there. As we go from our new cutoff, right here, our new alpha level here of 0.025, that's 95%. And in the social sciences, we consider that alpha level to be in the acceptable range of where we can make an error and find it acceptable, okay? So like I said, that means that 5%, I'm wrong 5% of the time when I'm counting it as right, okay? I'm wrong 5% of the time. Well, as we move to this side, as t moves this way, okay? T moves this way, and the numbers get lower, okay? I'm going to accept the null hypothesis. Well, the formula for t, for all intents and purposes, is that t equals mean of 1 minus the mean of 2. It's the same as z divided by the standard error. We're going to be calling it the pooled standard error. We're going to be doing something a little bit different. Okay? But as you can see, what are we saying? That the difference between one mean and another mean is so small that when I do this math, I'm going to end up with low numbers. See, this is where the lower numbers are. That's why I'm accepting the null hypothesis as I go this way. As one of these numbers gets high and the other one is low, okay, and I do the subtraction divided by the standard error, my numbers are going to get higher, and I'm going to reject the null hypothesis, meaning something is happening here. Something is happening. Do you get what I'm saying theoretically here? Am you picking this up? All right. Let's write down a problem. Guess what? I'm not going to use health stations anymore. And we call this hypothesis testing. Now we're going to actually test a hypothesis. All right. Oh, I am going to use health inspection stations. What do you know? I just can't get away from those. 25 health inspection stations in the state were tested. 25 in the state were tested. And the mean score of these 25 is 76.60. The standard deviation is 11.72. We're going to compare these 25 stations in the state with 25 national, across the nation, 25 stations across the nation nationally, okay? At the national level, 25 nationally. And the mean at the national level is 78.88. And the standard deviation is 15.58. Now we can compare means using a z-score or a t-score. What would I use in this case?
T.
T.
I'm going to use t because my n in each one of these is less than 30. Okay. The formula that I'm going to be using for t that I just flashed to you, okay, is t equals the mean of 1, and in this case we'll make the mean of the national, we'll put the national first just to make the math look nice, minus the mean of the state divided by the standard error pooled with a little p. Okay, this is the pooled standard error. You don't know how to do this yet, but we're going to show you how to do that. Okay, you know this part, right? And actually, if I didn't put the little p there, you know that part too, standard error. Right? Okay. We good to go? You need to know the formula for the standard error pooled is equal to the standard error squared of one group, the state, nationally. We'll change it around a little bit in a minute, plus the standard error squared of the second group. Now, just for the heck of it, let's make this the national for art, and we'll make this one the state. Okay. What is the formula that we're going to use here? What is the formula that we need to know for standard error? Dwayne?
Standard deviation divided by square root of n.
It's the standard deviation divided by the square root of n. That doesn't change, does it? That's like a constant. We know that score. Okay. So what we need to do then is to find the standard error for the state and the standard error for the national. And we've got everything that we need for both. Okay? The standard error of the state, let's go to the state data here. Okay? It's the standard deviation, 11.72, divided by the square root of n, which is the square root of 25. Right? There's 25 in the state. That's our n. And this is n. N. Okay? And this is going to give us 11.72 divided by 5. The square root of 25.
2.34.
Way to go, Chad. What is it?
2.34.
2.34. Correct. Now we need the standard error of the national testing station. And our standard deviation here is 15.58 divided by the square root of 25, which is the n is the same in both. We want to try to keep the number in both standardized. If you're looking at 25 in one, you want to look at 25 in another. Okay, and this is going to be 15.58, get ready, divided by 5, which comes out to 3.11, right? I jumped the gun on you that time. Okay. Let's go back to this formula here. Okay? We have the standard error pooled equal to the standard error squared of national plus the standard error squared of the state. So that's going to be the standard error pooled is going to equal the square root of, well, what is the national? 3.11? 3.11 squared, okay, plus the standard error of the state, 2.34 squared. Okay? Now, so you're going to have to take the square of each one of these numbers and then and add it before you take the square root. Okay? So the square of 3.11 is 9.67 plus 2.34 squared is 5.47. Add these two numbers together, and you're going to get the square root of 15.34. And the standard error pooled is going to equal what is the square root of 15.34, which is 3.89. Everybody see where I've gotten this from. This is just plugging these numbers in.
Wouldn't that be 15.14 and not 3.4?
Oh, okay, 15, okay. It very well could be. 15.14 you got?
Yeah.
I'll go with that. So what is the square root of that?
3.89.
Oh, 3.89. Okay, so I miswrote my number. 3.89. So standard error pooled is 3.89. Excuse me. Okay. Have we solved the problem? No, because we've got a major component done. The most difficult part is done. We know that the standard error now, okay, pooled, we know the standard error pooled now is 3.89. And we've got everything now we need to do this problem. Okay, the standard error pooled is 3.89. What is the formula that I gave you? T is equal to the mean of, let's say, the national minus the mean of the state divided by the standard error pooled, right?
Yes.
And this is going to be, what is the mean of the national? 78.88. Okay, minus the mean of the state, 76.60, divided by the standard error pool, 3.89.
That's your answer?
No.
Oh.
We're almost there, though.
Gosh.
Now, just before we go any further, can anybody just look at these numbers right here and tell me, are we going to end up with a high number or a low number?
Low.
And if we're ending up with low numbers, what most likely are we going to be doing? Accepting the null hypothesis. Very good, Wendy. That's the trend. We don't know with degrees of freedom yet. We haven't looked. But to me, my gut feeling is telling me that this is not looking good to say that they're different. What it's looking good to say is that they're more the same than different. So let's do the math now. Let's subtract this and divide it by 3.89. So you should get t equals 2.28, if my math is right, divided by 3.89. And my answer is 58. Okay, now I've got to go to my table. What's that? Question? Lazarus, you have a question?
Oh, no, I'm good.
You sure?
Yes, sir.
Okay, so you can come up to the board and do the next problem?
Sure.
All right, then.
Hope you got a lot of film.
Let's go back to my table. The one thing we don't have here is we don't have degrees of freedom, do we? We need degrees of freedom yet. We haven't calculated that, and that's the easiest thing to calculate. Degrees of freedom is equal to n minus 1. What's n minus 1 here?
24.
24. 25 minus 1 is 24. Okay. So I know my t value here is 0.58. So if I go down to 24 degrees of freedom, just on what the table shows me, if you look at this table, and if we could zoom in at the table, let's zoom in at the table. Good. Okay, here's 24. Here's 24 degrees of freedom right here. Okay? For this to be significant, my value for t has got to be at least 2.06. But as you can see, it's significantly less, isn't it? 0.58 is significantly less. So which way am I going here? Well, if in fact here at 80 at 0.10, and we got to go half of that, so at 0.10 we're at 80% confidence level at 0.10 because we'd have to multiply it by 2. We're not even at an 80% confidence level. We're significantly less than that. So what are we saying? If we go to this little drawing here again and zoom back out,
Saying that's way off. It's not close to the mean.
no. We're saying that the means are very close, so close that the difference isn't significant, meaning nothing is happening anything different here.
Okay, you lost me.
Okay?
Okay, going back to the table.
Go back to the table.
So going 24, and you said it's not close to 26 because we're doing 95%. So
Well, let's go back. Let's just look at the table again. Okay? Here in the table, at 24 degrees of freedom, for me to be significant at the 95% confidence level, which is this column right here, I've got to have a t value of at least 2.06 or greater. For me to
Be 95%.
reject the null hypothesis.
Oh, okay.
For me to reject the null hypothesis. Rejecting the null hypothesis means that nothing happened. Means that something happened here. We're rejecting the null, which means nothing happened. We're saying that something is happening here. But that's not the case.
So if it would have went, let's say it went the other way, you would have rejected it?
That's correct.
Okay.
And if you should have put on the top of your table, in the upper right-hand corner, you should have written the word reject, and the upper left-hand corner, accept.
Actually, I didn't do that, though.
Did you do that?
Yes, sir.
Okay, and you see that should make it plainer. Now, question.
No, we just want to make sure on the 95%, that's kind of like the standard.
That's the standard in the social
Okay.
sciences. But, you know, there are certain things we might say in the social sciences I want to be 99% sure of. But usually we're at an alpha level or significance level of 0.05. Okay? If you look over here, Lazarus, you can see that our two means are not that much different. You know, considering we're talking about, you know, if you look at it like money, you've got $78, I've got $76. Do you have a lot more money than I do? Are you richer than I? Are you significantly richer than I am? You have significantly more money than I do? So you're not that much different than me.
Right.
Dwayne?
Now, I might be wrong about this, but isn't this kind of an example of how you said, like, we explain very simple stuff with extravagant concepts? Because that seems to be, I don't need to do all that math to be able to tell you that you're not that.
Well,
much different.
but you never can be too sure. In other words, you have, because what's going to make it different? What if this number down here, okay, the standard error was 0.02?
Reject it.
Now, what's going to happen to the difference of my mean? They're going to be greater. It's going to be greater just by changing the standard error. You see what I'm saying? So you just can't go by, you know, we call that empirically, what we can observe. You just can't say empirically, this looks like we're going, you know, I could say that, you know, at 3.89, this doesn't look good to me. And in fact, just for the heck of it, just for drill, what would it be if this were 2? Could someone do the math? And let's just see how much this changes the answer. If my Pool's standard error was 2, can somebody quickly calculate this and tell me what my value for t would be?
1.14.
What is it?
1.14.
1.14? 1.14. Now let's go back to the chart and let's see if this makes a difference. And frankly, no, it doesn't. But at least we're closer to being on the chart right now. We're closer to the 80% column here. We're getting closer. You know, at 24 degrees of freedom, we are getting closer. Okay? So you really can't ultimately make that decision. Let's do another problem. Just like this. Now, I am going to be asking this on an exam next week, okay? A quick exam like I did, 3 problems. You know, the better that you do in those exams, you know, the more that I have, the better your grade, right?
Nope.
All right. Here's the next problem. All state inspection stations. No, I'm only kidding. Definitely we're not going to do that. We're going to take something a little bit different, being that we're talking about the Sweet 16. Okay? The Sweet 16, we're going to talk about the height of Robeson County youths. Okay. Okay, examining the height of Robeson County youths. Okay? Utes. Examining the height of Robeson County utes, we find that, so we have Robeson County, Robeson County,
Red jacket.
okay? In Robeson County, we find that we have a mean height, and go with me on this decimal. I'm going to say it's 5 foot something here, okay? Our mean height is 5 foot 0.46. Or so let's just say 5.4, 5 foot 4 inches. That's not what it is, obviously. It's more like 5'5". But let's say it's, you understand what I'm saying?
So it's
Height, wait,
5.4.
let's like it bob down. This is their height, 5.46. Forget about feet and inches. Okay, and the standard deviation,
Yeah, it doesn't. Yeah.
we need the standard deviation is 0.584. 0.584. And we're looking at people in our class. So let's see, what was my N? My N, there's only, in my class that I'm teaching here, there's only 9 students, let's say. We'll make the square root part of the problem real easy. 9 students. So this is Robeson County, okay? And now we're going to compare those to 9 students nationally. Okay? And at the national level, the mean is 6.09. Wow.
Must be cheap.
Something you could tell right now almost empirically that we're probably going to reject the null hypothesis, right? We've got a pretty big difference here. But let's see what the standard deviation is, et cetera. Standard deviation is 0.645. Okay? And N is 9. So in relation to this N being 9, I'm going to be using a t-test to check these two groups to see if they're different or if they're essentially the same. Okay. My formula is T is going to equal the mean of 1, let's say that's the nation, minus the mean of Robeson County, divided by the pooled standard error. That look familiar to everyone? I'm going to erase it, okay? The first thing I want to find out here is I want to find out my pooled standard error. That's something that I really need. And the formula for the standard error pooled is equal to the square root of the standard error of the nation, and that could be 1, it could be J. What I'm putting down here is my own note for myself, squared, plus the standard error of the county, R, squared. Now for each one of these, for the county and the nation, I have to find out what my standard error is, right? I don't know what this number is. So I need the standard error. The formula for the standard error across the board is, the standard deviation divided by the square root of N. So let's do this. We'll make this the nation one. And this is the standard error of Robeson County. Okay, in the nation, the standard deviation is 0.645 divided by the square root of 9, which is 0.645. Get ready, Chad. Divided by 3 is equal to
0.215.
0.21. How's that? Okay. And then down here for Robeson County, our standard deviation is 0.584 divided by the square root of N, which is 9, which is 0.584, Chad, divided by 3. And that's equal to
0.19.
0.19. Everybody got that? Okay, I'm going to erase what's on the bottom here so I can put those numbers that we just found into our pooled standard error equation. standard error pooled is going to equal, what is the standard error of the nation? 0.21 squared plus the standard error of Robinson squared is, do I have the numbers right, 0.19 squared? And now standard error pooled is going to equal, let's square those numbers and keep them under the square root, 0.03 plus 0.04 plus 0.03. Right? And that's going to equal the square root of 0.07. And that's going to equal 0.264. Sound right? Did everybody get that? Latika?
How do we know when to use 2 decimals versus 3 decimals?
Whenever you want to. We could just use 2 here. So now we have the standard error pooled. Did everybody get that standard error pooled? Okay. Now let's go back to our formula for T. T is going to equal the mean of nation minus mean of Robeson County divided by the standard error pooled, and that T is going to equal, what was my mean of the nation is 5.46 minus, I'm sorry, I have that in reverse. That should be 6.09. It doesn't matter because we don't use negative numbers here, remember? Minus 5.46 divided by, what was my standard error pool? 0.26. And that's going to be 0.63, I think, divided by 0.26. And T is going to equal 2.38. Now, what else do we need here that we haven't determined? If we're going to look at the T table, we need to know the value for T, we need to know our percentage, and we need to know the degrees of freedom, right? So our degrees of freedom here is n minus 1. So degrees of freedom are going to equal 8, right? 9 minus 1. Let's go to the chart and see where we are.
You're over it.
We in the reject.
We're rejecting, huh? Let's see. So with 8 degrees of freedom, okay, here's my 95%. Okay, anything higher than 2.31, I'm going to reject the null hypothesis. At 2.31 or higher, I'm rejecting the null hypothesis. Lazarus, you see that?
Yes.
So the answer to your question, how do you write it? Do you just write null rejected, and that would be the answer to that question?
The answer is T equals 2.38. At 8 degrees of freedom, I will reject the null hypothesis. Frank?
Okay. When I was doing this in the beginning, my standard error for the national one was 0.22 instead of 2.1 because of the decimal I rounded to.
Okay.
So my numbers actually at the end ended at 2.1.
So you now are
So
on the you're still 2.1 is still greater than, is it still at least at 2.09?
Yeah, I'm between 90 and 95%, but
No, you're not. You're at 2.1, you said. Your T is 2.1?
Yeah.
Well, 2.1 is greater than 2.09. It's like $2.09, $2.10.
We're not dealing with 2.09. We're
not
dealing
at
with
19.
Oh, I'm sorry, at 8. At 8, I'm sorry. You came out to 2.1?
Yeah.
So, yeah,
So
by
would I-
rounding off, you became,
Would I get that wrong by accepting it?
and you got that because where did you start rounding off?
I think I went to 3 decimals and it was like 0.215, and I rounded it to 0.22 instead of 2.1.
Yeah.
and that changed that whole.
Well, you're very close. I would not take off for that. I will make sure that on the exam, the delineation is pretty clear.
So do you want us to round up or just drop them?
I think that it's probably better to round up. Round up than round down.
Well, what about not rounding at all? Is what I'm asking.
Oh, if you don't round at all, then you're going to be in much better shape by not rounding.
And just dropping the
Yeah.
other places?
Mm-hmm. Just let them be what they are. But let's just go and let the computer do our work for us now. Make things a little bit easier. Any question, first of all, any question on what I've just covered? Questions?
I just want to clarify the answer.
Yes.
You said T equals 2 point, whatever it was, at 8 degrees of freedom, I will reject the null.
I will reject the null hypothesis. What if I said I will accept hypothesis 1?
Accept hypothesis 1? Well, you know, how do you know what it is?
Well, I'm just saying, if there's a null hypothesis, there must be a hypothesis 1.
Right.
Okay, so I'm just saying the same thing, only looking at the positive side rather than the negative side. Anything? Any other question? Okay. Okay, some of this requires a little bit of a leap of faith. Okay, this is your SPSS page. We're using SPSS 14. I don't know what version you guys have at home. But a lot of times, we have to recode variables. Like, let's say I was doing a survey, and I want to do a survey on the death penalty. And I'm going to go to 2 churches in Robeson County. I'm going to go to the Baptist church, and I'm going to go to a Baptist church, and I'm going to go to an Episcopal church. I know you have an Episcopal church in Robeson County, Lumberton. And I want to get attitudes of parishioners on the death penalty. Now, the Baptist church I'm going to is a very small Baptist church, and there's less than 30 members there that day. This is a small Baptist church. It's one of the tiny ones. It's not like Union Chapel Road. It's a big one. That's a big one, isn't it? Union Chapel. It's not like that. Okay, so I'm going to look at attitudes towards the death penalty. Now, I'm going to say, I'm going to ask just one question. Are you for or against the death penalty? So now, did you notice when I did the t-test, we call data like that robust data. Yes, I'm for it. No, I'm against. I'm for it, against it. I'm against it. I don't like it. I hate it. Robust data. You notice I can't do any calculations like that with robust data with a t-test. So I can recode my variables into numbers. And I could make yeses 1s and no's 0s. I'm for it, yes. I'm against it. No, I don't like the death penalty. So let's say that this is my first column over here. There we are. Okay, I'm at the Episcopal Church, and I ask, are you for or against the death penalty? And these are people that are, they don't want the death penalty. Okay. Oh, we have no 10s, do we? So I'm just putting in yeses and nos here, with 0 being no and 1 being yes. Okay, and this here is, so I'm going to code my variables. Go to my variable view here, and let's give this a name. We're going to call this, what did I say this was Episcopal? Come on.
Yeah.
Episcopal. Episcopal. All right. And over here, this variable here, let's see, variable view. We're going to call this Baptist. Okay. They are for the death penalty. Now, you know, this is a good thing for you, Dwayne. Looking at the raw data, can you tell me if I'm going to accept or reject the null hypothesis here? No, you can't. But you see, the closer, I guess, we get it to where we look at the mean, where we actually calculate the mean, et cetera, then you'd be able to better tell me. But when we're looking at large amounts of raw data, we can't really tell from the raw data if we're going to accept or reject. Okay? So now here we've got how Episcopals and Baptists feels about the death penalty. All right. Now what you do, and you should be writing this down because you're gonna have homework. Homework problems. You go to analyze, compare means. Analyze, compare means. Paired samples t-test. Paired samples t-test.
Compare me.
Paired, P-A-I-R-E-D, paired samples. There are two samples that are paired. All right, they're both about whether you like or don't like. What did I say? Did I spell something wrong again? Did I say P-E-A-R? No, I did not. Don't make me think that. I think that if you just click one of the variables, both of them should come over. No, you have to click them both. Okay. Now we've got our two. We've got our two groups. Our two groups. We've got Episcopals and Baptists. Oh, I spelled Baptist wrong. That's what it is. I get what you're laughing at now. All right. Now, just for that, I'm going to cancel the whole thing and change it.
But we're laughing at how you said
B-A-P-T, right?
Yeah.
B-A-P-T. Boy, oh boy. Thanks for embarrassing Dr. G. You can't see
You can
it?
edit it.
You're lying to me now. I know you're lying to me. Okay, let's go to analyze. Compare means, because that's what we're doing, and a paired samples t-test. Here are two samples. And what do we want to see? We want to see, are these similar? Are they the same group? Nothing is happening? Both Episcopalians and Baptists think the same about death penalty? Or do they think differently about the death penalty?
You say you have to click both of them?
Yeah, you do have to click both. And then it pairs them together. All right? So you might have a number of variables here that you might want to pair up. So you got to click the ones you want to pair up. Okay. I don't think we're going to need any options here. Let's just see what comes up here. Okay. Okay, so here we got our, look how fast this is done. All right, I mean, it's been done here.
Amazing.
Here's our two samples, Episcopal and Baptist, and you're right, the resolution here is not that clear. The further you go away, it is. But here's our mean. There's our mean. I didn't tell you any mean, did I? Calculated the mean. So what we're looking at is the difference of the means. Right, now you can see there's a difference here, can't you? Mm-hmm. Okay, here's our standard deviation. Well, you know that the computer needs a standard deviation. And n, does it know n? Mm-hmm. Of course it knows n. Here's n, 22. We had 22 responses compared to 22 responses. Okay, and here's the standard error. So I know I got this divided into the difference between this. Okay. They put some correlations over here, and we're not doing correlations. We're just going to be looking at over here the significance, and I got to move my thing over. Okay, look at how this works out. It's significant at the 0.05 level. Now, here we're going to be looking at alpha of 0.05, not 0.025.
Why is that saying Z-tailed in parentheses?
Two-tailed.
Oh,
Two-tailed test.
Okay.
Two-tailed test. It's looking at both tails. Your book only looks at one tail, right? So we had to cut the number in half. This is looking at two-tail. It's doing the calculation for you. So what is the significant level that we look for? Well, we look for 0.05, don't we? That's the least that we look for over here. And here we got 0.05. So are we accepting or rejecting the null hypothesis here?
Rejected.
Rejecting.
Say that again, Dr.
Are we accepting or rejecting the null hypothesis here?
I understood that part, but how do we get to?
Well,
Based off.
okay, let's just go back to my chart up here. Let's go back to my chart up here. All right. Now, we have to take the leap of faith here because we're not exactly looking at apples to apples, but stop right there. Okay? We're looking at the .025 column here. Okay? That's what we're looking at. And that's significant at the .05 level in a two-tailed test, and that's what this is. Okay? This is a one-tailed test, two-tailed test. So here it's .05, here it's .025. Okay? But be that as it may, let's say that this is, for us to accept the null, it would have to be greater than .05, this alpha level. It would have to be greater. If it was greater than this, higher than this number, we're going to accept the null hypothesis. At this number or lower, we're rejecting the null hypothesis. You don't have to find that the value for t. It tells you what the value for t is. Whatever that number is. What is it?
2.084.
2.084. So it's telling you at 2.084. So, all right, let's look at the chart. What was our degrees of freedom here? We had how many? 22, so it's 21. Let's go to 21, down to 21. At 21, at .025, we need to be at least at 2.08, and this is 2.084. So do you see where we are? So we are going to reject the null hypothesis. Is there a difference between how Baptists feel and Episcopalians feel? Yeah, there is. Okay? Let's just look at another one. Let's make up another one. Yes, sir.
As we go from doing it by hand as a 1T to looking at it here as a 2T, I do understand. I guess my question really is,
There's a question?
when I look at the T equals .2084 from the computer from the two-tail, why wouldn't I come to the book and look up under the two-tail at 95%?
Well, you don't have it. You don't have a two-tail here. This is a one-tail test. So you're going to look at, yeah, I mean, that's what we just did. But why would you have to look at the table at all? When you're looking at the computer, is doing it all for you. It's coming exactly to the number that you want to find in that column.
Okay, I guess that leads to the next question.
Why are you doing it by hand?
No.
Oh, well, that would be a sensible question. What's your question?
No, just really trying to understand when I see that .05.
Yes.
Knowing that when to reject and when to accept, I guess.
Anything greater than .05, you're going to accept the null hypothesis. Anything at .05 or less, you're going to reject the null hypothesis.
Okay.
Anything greater?
Anything greater than .05, you're going to accept the null hypothesis. Anything at .05 or less, you're going to reject the null hypothesis.
All right, that answers my question. Right.
Okay. Now, what I want you to do for homework is 30 of what I just did. 30, make up the 30 data. Okay, make up the data.
Oh, okay.
Calculate it like this and tell me if you're going to accept or reject the null hypothesis. And give me your printout. 30 is not a lot. Look, I'm going to do another one right now. I'm going to come up with two more variables here. Yes, Latika.
No, I'll wait.
You wait? Okay. Yeah. Maybe the answer. Let's come up with another variable here. Let's come up with North Carolina. Let's make it simple. And South Carolina. And we're going to be talking about in 22 counties in North Carolina versus 22 counties in South Carolina, how many arrests there were for felonies last night. Okay? How many arrests there were for felonies in 22 counties in North Carolina and 22 counties in South Carolina last night. So this was in Robinson County, and this was in Scotland County. And this was in Brunswick County. That's where I live.
So Tika's life, because she lives in Cumberland County.
Cumberland County. Well, we had 12 in Cumberland County
no
last
way.
night. Where do you live?
Fayetteville.
In Fayetteville. That's Cumberland County, isn't it? Yeah. Okay. All right. And where do you live, Ray?
Durham County.
Durham County? 15 in Durham County last night. Ladies, any different county? Robinson County, we got that up there. Okay. And then we've got some real rural counties. We got like Buncombe County and what's those ones, those western counties where there's the frontier counties, basically. There's less than 6 people per square mile. We got some of those. And then we've got, some minor reprobates here and there, By the way, if a dot in a column, it will always be counted as no data or 0 there. So we're just gonna put a 0 in there. Okay, and here we've got 4, 3, 8, 0, 1, 2, 3. Okay, that's North Carolina, and then South Carolina we've got like Horry County.
Williamsburg.
24.
24. All right. What did you say?
Williamsburg.
Is that where you're from?
Yes, sir.
0, because you're a good kid.
Oh.
That's Sasha. We go back. Well, all right, what other places? Well, we have a couple of other places, and
Florence County.
Florence.
Florence, about 25.
There's one county had 50. Must be where Columbia is. There was a riot there in Columbia last night. Okay, now we've got our counties. Okay, we're going to go to analyze, compare means, paired sample t-test. We're going to get rid of these guys. Just highlight them, get them back. And we got North Carolina and South Carolina. Okay. Okay.
And he wants 30 of those.
All right, we could just, here's our N, 22. Okay, our mean, 5 and 3. That's a big jump there, right? Okay. Well, actually, but it's not going to be that much of a jump because of the standard error is going to equalize it. And we're at our significance here is at 0.34. Are we going to accept or reject the null hypothesis?
Accept it.
Accept it.
Accept it.
Hold on, wait. You said if it was negative.
Oh, never.
Well, some people are saying, but excuse me, Lazarus, we have some people saying reject and some people saying accept. And reject and accept. It's greater than 0.05. Are we going to reject or accept? Accept the null hypothesis. Nothing's happened. There's no difference between North Carolina and South Carolina. Everybody who said reject the null hypothesis, stand up and drop down on the floor and give me 20 push-ups right now. All right, so you see, this is what I want you to do for homework. So, the golden rule here, if it's greater than 0.05, you are going to accept the null hypothesis. If it's at 0.05 or less, you're going to reject the null hypothesis.
Got you.
Let's take a 10-minute break.